Welcome to our NPTEL courses on the power quality improvement technique. Today we are going to discuss the operation and the control of this grid connected voltage source converter. This discussion is not restricted to the power quality because shunt active power filter or the D-STATCOM essentially is the grid connected inverter, and nowadays with the penetration of the solar inverter and other entities. So, and we have coupled the power quality issues with this distributed generation, and for this reason we require to have a heuristic discussions of this operation and the principle of the operation of the voltage source grid connected voltage source inverter. You know what happened, this topology can act also as a shunt active power filter at the point of common coupling. So, filters is required to be little higher side for the actively used as a active power filter, and it can be coupled with the distributed generation like solar and other entities mainly. So, then it can have the power to compensate the reactive power compensation. Apart from the reactive power compensation, it can compensate the real power. So, this kind of integrated topology is gaining advancement, and it has been this distributed generation and the power quality, both these issues are been integrated, and it looks like an integrated problem nowadays. And how it is been done, let us see. Generally what happened, this is the your grid point, and we say that it is a PCC, and if you wish to inject a certain amount of the reactive or the active power with the presence of this active source in the DC link, then you have to have a PQ control. What happened? We have talked several times that PLL, generally you have this point, it is called a point of common coupling, and from there you have a PT generally. This will measures the voltage, and from there essentially you will generate the theta. That is very important component, and also we want that to transform all the quantities into the DQ frame. What is the DQ frame? You know very well that you got a 3-phase system ABC. From ABC you go to the alpha beta frame. This is nothing but a 3/4 to resolving into the xy coordinate, that is the alpha beta. When alpha beta is rotated at a synchronous speed, or the frequency that is generated by the PLL, and instant position is generated by the theta also, then this frame of reference, then the fundamental component looks like a DC parameter, then tuning of the PI controller and other issues become easier. And for this reason we have told several times that SRM method, this is basically an SRM method to convert into the ABC to DQ frame of reference. Now, see that this is the PQ reference technique. Then you have P star. From their reference you may know that from the irradiation and all those things, you may know that you require to supply certain amount of the real power to the system. If it is not present, then P star can be 0, ultimately you require to sink certain amount of power from the grid to maintain the DC link voltage, and thereafter you will have DC star and DC. So, this is the your active power controller. Similarly, you have a reactive power controller. Generally this has been used frequently for the D statcom. So, you require to inject a certain amount of the reactive power. So, you got a Q star and actual Q will be measured from the from this current and voltage, and you also check that this voltage at this point is healthy or not. If it is healthy, then with or in the length of the tolerance, then Vx is the voltage at the point of common coupling. If it is sacked or swell, then this value will be different, and ultimately what happened, you got this ABC, from there you got a dq, and you from this P and P star, VDC and the VDC star, this is these are the real power component, and ultimately you will generate that IT star. Similarly, actual ID measured after transformation will be this, and it is been subtracted. Thereafter, you will feed this error into this PI controller, and same way there will be a cross term. So, D will be multiplied with the omega L and will be subtracted from Q, but both are the subtraction, that ultimately the addition. And similarly, this Q reference, what has been generated from the voltage sags and the reactive power compensation, Q star has been generated, and that will be subtracted from the IQ, and again it will be multiplied by omega L, and that will be again add up with that. Ultimately, this will be the VCD, the reference voltage for the after compensations. And similarly, by multiplying omega L and you add up this component, this is generally this will be, both will be minus sign, and thus you get VCQ. Generally, if there is a presence of the real power has to flow this way, and it is minus because reactive power required to be compensated. Ultimately, you have to inject the positive bar. So, you got again from theta, this theta will be fed again into the dq to ABC block. From there, you will generate this control signals for the PWM. We have already discussed PWM in our discussions. So, different kind of PWM technique can be applied depending on the level of the inverter, and then it will be triggered this devices. This is called, this is the way to control your voltage source controller in grid connected way with active source or without active source. With active source, it has a power to compensate, power to inject the real power. If there is no active source, it cannot inject the real power. So, if we talk about the distribution system, and we may have a simplest system, that is the 2 level inverter, and then what happen, you may have a DC source here that may be a solar, and you are feeding this load. So, it is not a grid connected entity. So, there it is quite easy, because then you can choose a reference and you force that current to track that reference. And generally, once power flows from DC side to the AC side, so we say the inverter operation, that is what your household inverters are. And what happen, when your grid is off, when it generally it is there when your grid is off. When your grid is on, then you may be charging the battery. This become then load, and ultimately you require to take power at unity power factor. Then it becomes a active rectifier, and you will be charging at a unity power factor. And there also you require to control the P and Q. So, it has a different mode. Once you are sending power DC to AC, then P become positive, here actually P, if it comes from the grid. So, it becomes a load, that P become negative. So, this is the typical sine wave modulation technique we have discussed in detail, we are just not going to this. So, this is the based on this where the logic is that the modulating signal, this is VMC, if it is greater than V triangular, then or V carrier, then the particular phase is switched on. Based on that, you have a 6 gate signals for 2 level inverter, VG1, VG2, VG3, VG4, VG5, VG6, accordingly pulse width duration will change, and ultimately these are the phase voltages. This is VAN, VBN. If you add these phase voltages, then you will get the line voltages, and ultimately you can find that this is the line voltages of this PWM nature. Please understand that you require to provide an inductor. Why? Because ultimately this sine waves volt area curve matches with this sinusoid, matches with the pulse width modulated waveform, but there is a instantaneous variation between the PWM voltage and the voltage at this point. So, for this reason we require to provide a buffer inductor, and thus the calculations of the LF or the inducted side inverter and the grid side inductor comes into the picture. Now, the grid connected inverter. So, ultimately what happen, you require to synchronize, because at this point, please go back, you can see the voltage is this, maybe at peak, you know. So, what happen? So, at this point voltage have some value and this point voltage has some value, and you require to inject the current, because ultimately you are giving this kind of pulses, and instantaneous current definitely will be flowing, depends on, let us go to the take the whiteboard. Basically when it is switched on, you get VDC by 2 minus, if it is half bridge converter, minus Vm sin omega t equal to essentially as L di dt. So, you can integrate this value and get the value of I, and for this is the purpose of the PI controller. So, ultimately you can see that injecting current, it has a dynamics. So, controller has to ensure the first switching, so that you want a particular sinusoidal waveform to follow, and that will be followed, and ultimately you require to inject a particular value of the power, that is given by V1 minus V2 by x into sin delta. So, this is something we require to control. So, this is a way we require to control the grid connected inverter, and if it acts as a active rectifier, sometime it acts because you may have a bulk of the batteries to be charged. So, you require to be charged in a sinusoidal fashion. So, it will be like this, and reverse can also be true, because you may have you may have a peak management control, especially in evening. So, you want to feed the power from the storage element, or you may have a solar, then power will flow back from the DC side to AC side. Now, let us see. So, this is the case where power flow via VSC, and this is a power flow, and ultimately if it is from the grid side to the inverter side, there is active rectifier, and if it is reverse, is the inverter operation. And also there is a issues of the power factors. For example, if Pg, that is a grid power, is greater than 0, so power is flowing from the grid, from the converter, and that is your 1 and the first quarter operation. And generally if it is a leading power factor, then you have the operation range of the 270 to the 360 range, that will be the operation range. On the other hand, in this coordinate you got the Pg positive here, but you can have a negative power factor, and where we talk about, so this is the angle it will vary. So, it is within the 0 to 90 degree. Similarly, there is a second quadrant that lies in between 270 to 180 degree, and where power will be flowing back from the grid to the source, and for this reason you can see that net power received by the grid, and thus it is from the solar to the grid maybe, and you can have this operation. Accordingly, you will fix up whether you want a leading power factor operation or the lagging power factor operation. That comes into the picture when whether you want to have a power quality issues, that is how much reactive power you require to compensate. See, in my discussions I am silent about the harmonic power. I will be take out these issues separately, that is shunt active power filter, and that is one of the major issues it is in case of the power quality. So, for this reason, this is the logic, this is the grid power is given by definitely for the 3 phase system, in terms of the phase values it is 3 Vg Ig cos phi g, and cos phi g can be any value 0 to 360 degree, and where phi is the angle between the Vg and the Ig, the phase angle. So, generally if this voltage VDC is the voltage and it is E, that mean what happened, very simple, that VDC voltage is more, that means it is charging the battery. So, IDC is positive and thus Pg is positive, and the power flow thus it is to the grid to the load, and it is a rectifier mode. Of course, we require to take a unity power factor operation. Same way, if you have that E is greater than VDC, then IDC is negative, definitely this value is more, definitely current is flowing to this direction, and thus Pg is negative. So, it is in the inverting mode, and maybe this is not there in case of the shunt active power filter, because it does not compensate the real power, and thus this concept does not arises, but it require to boost up the DC bus voltage some extent. So, E VDC E equal to VDC, then it is in a floating mode, then IDC equal to 0 and PDC also equal to 0. So, no power flow between the DC circuit and grid takes place. Now, there is an important transformation, as I was telling you, alpha beta to ABC to the alpha beta FEM. This is nothing but a 3 vectors resolved into the xy coordinate, we say it is alpha beta. Then once alpha beta has been rotated by the synchronous frame, then it becomes the DQ frame of reference. So, this is the transformation. Once you have the ABC coordinate, this is the pictorial phasor representations. So, this is the A axis stationary, and we aligned A with the alpha, and thus you got a B axis and you got a C axis, and it is rotating with the speed of omega. So, all the vectors you can resolve into the alpha beta frame, and by this transformation where x bar is basic will be x alpha plus j beta equal to k will be a constant, where k is 2 by 3, this x a plus x b you have to multiply with the 120 degree and you have to multiply with the 240 degree or minus 120 degree, where k equal to 2 by 3, x alpha beta equal to 2 by 3. So, you can get this transformation in this way. So, alpha beta equal to, it may be voltage or current, anything. So, this transformation is called the Clark transformations, and thereafter, since x alpha beta can be multiplied by the synchronous frame of reference, then it becomes the dq frame of reference, that is x dq e to the power j omega t, where theta equal to omega t, and thus x alpha equal to x t cos theta minus x q cos theta minus 90, that is nothing but a sin theta. So, x t cos theta minus x q sin theta. Similarly, you can write x p equal to x t cos theta minus 90 plus x q cos theta. So, it will be x t sin theta plus x q cos theta. Thus, the transformation from alpha beta to dq will be this, that is cos theta minus sin theta cos theta. So, this is a transposition matrix. Ultimately, if you couple these two transmissions, so you can have directly ABC to dq and vice versa. It is called, if you go by reverse, then it is called the reverse Parkes transformation. So, this transformation is called the Parkes transformation, while converting to the ABC to the dq frame of reference directly. So, you got a this k will come out here, and you got a cos theta minus 120 degree and cos theta minus 240 degree. Similarly, sin theta minus 120 degree minus 240 degree into XPC. So, in this way we can compute the alpha beta to dq frame or directly ABC to dq frame, and if you take the matrix inverse of it, then it is called the reverse Parkes transformation. Now, we require to come across few terms, as I was writing in a whiteboard, that this voltage is varying and this is the PCC, and there is a ultimately this is a part of the compensator, that is I am writing as C. It can be shunt active power filter, it can be active rectifier or anything else. So, this is the lump resistance. We have not connected this resistance physically. All the resistance in series has been lumped out here, and this is the inductor connected into the circuit. So, what happened? We can read all these equations for current source and the capacitor. In case of this solar model, it fits quite well, or that why it is so, because ultimately C dV dt is essentially gives you the I. So, I we can write as a dependent voltage dependent current source. So, or solar is also same thing. So, anyway, so for this reason we have put it as a dependent current source and capacitor. Thereafter, you got IDC. So, if you combine this two part, this is the AC part. If you go back, essentially this part is this part is your DC part and this part is AC part. Just we have replaced like this. This part is AC part and this part is DC part. So, applying KVL across the PCC, and this we write as a G and C trans as a converter. So, this is a single notation representation, it can be ABC minus Vc. Thereafter, this is the resistance part of it, thereafter inductor part of it, and by having a Clark transformations, we can put these equations into the alpha beta frame, that is your Vg alpha beta minus C alpha beta equal to Ri alpha beta plus L di dt. Then we go for the Parkes transformations and convert into the dq frame of reference. Then Vg alpha beta equal to Vg dq e to the power j omega t, C alpha beta equal to this compensated or the converter's voltage dq frame of reference j omega t, and where this current in alpha beta can be transformed to dq by I dq e to the power j omega t. So, substituting this equations in equation 2, so you essentially get the equation into the dq frame. So, it is Vg dq e to the power j omega t minus C dq e to the power j omega t equal to R dq e to the power j omega t, and with L dq e to the power j omega t. Minded, I told you that DC in dq frame the AC quantity looks like DC parameter, but it is a transformation. So, these quantities are time varying, please note that, and for this reason its differentiation exists. So, I have been asked several times by the students, sir, once you are operating in a dq frame, so how this parameter preserves, because it looks like DC. But you note that these quantities are essentially the time dependent. So, differentiation exists. So, R I dq e to the power j omega t plus j omega L dq e to the power j omega t plus L dq e to the power j omega t. Ultimately, you divide e to the power j omega t, that is nothing but the theta by both sides. So, you get the equations in case of the dq frame of reference, that is Vg dq minus Vc dq R I dq plus j omega L I dq into L di dq dt. So, this is the equations. Now, expanding these terms, Vg is essentially we can write its d axis component, and to show that d quadrature axis component is at 90 degree. So, you have multiplied with the g. Similarly, for the converter voltages Vcd plus j Cq, similarly I dq equal to Id plus j Iq, and substituting the 4 and rearranging them, Vg minus Vcd equal to R I d minus omega L I q plus L d I q dt, and thus V g q minus V c q equal to R I q plus omega L I d q plus L d q dt. So, this is the equations you will get in case of the control loop, and you see that these are coupled equations, because I have shown in your, please go back, that once I have shown this control algorithm here. So, here there is a cross term, you have multiplied with the omega and you have added up. So, this is your omega L and this is the cos term and been added. So, similarly, this is your cos term being added. So, in this case. So, for this reason this is the q axis equations, but there will be a term of I d, and this is a g axis, this is a d axis equation, ultimately you will have a cos term with a minus sign. So, then we have the dynamic equivalent of the voltage source converter in the dq frame of reference. So, instead of the A, B, C, you have just only 3 parameters, This is the DC side, that has no change, but in AC side you have, this is your grid voltage in the D axis, that are resistant, it does not change, you got an inductance, that is L. Now you have an extra term that looks, that is a voltage. You see that its polarity will be different for the different voltage, because this one is negative and this one will be positive. And for this reason you will have omega L I Q negative, and here it will be your positive. So, this is the representations for our case for this DQ representation. Thank you for your attention. We shall continue to the discrete inverter in our next class.